In this chapter, we're going to measure position of the values in a data set. This is called non-parametric statistics. We're going to compute and interpret z-scores. We're going to compute the quartiles of a data set, and we're going to compute the percentile, and finally we're going to talk about the 5-number summary. The z-score is one of our most important calculations in statistics. It tells us the relative distance of a variable's value in relationship to its mean within the data set. The z-score value allows the researcher to identify extreme values in the data set and compare the relative distance of the value from the mean in different samples. We're also going to be looking at the z-score to identify things like outliers. The z-score equation is the following. Z is equal to x, the value within the data set, minus its mean value divided by the standard deviation of the data set. The z actually tells us how many standard deviations x is from the mean. So in our example, the National Center for Health Statistics Studies states that the mean height for adult men in the U.S. is around 69.4 inches, with a standard deviation of 3.1. The mean height for adult women is 63.8, with a standard deviation of 2.8. Who is taller relative to their gender? A man who is 73 inches tall or a woman that is 68? Well, to answer that, we will put them in the z-score formula. For the male, the value of 73 minus 69.4 divided by 3.1 gives us the answer of 1.16 standard deviations from the mean. For the female, we put in 68 minus 63.6 divided by 2.8, and we get the following result, 1.57, and that is how many standard deviations 68 is from 63. In this case, the woman who is 68 inches tall is relatively taller based on the female gender. The male at 73 inches is not quite as tall relative to its mean. So we want to compare the z-score with the empirical rule, and this is going to be important especially for normal data sets. The z-score allows the researcher to identify values of the quantitative variable that are extreme relative to its mean. These extreme values are called outliers, and we're going to use that term a lot in this semester. So that's one of the terms that you want to hold on to. And we have a major impact on the calculation of the sample statistic. To identify potential outliers, the researcher calculates a z-score value for each observation in the sample. If the z-score value is greater than 2 or less than minus 2, the observation is considered an outlier. And so in a normal curve, we would see areas like this to be considered outliers under the empirical rule. Since the z-score is the number of standard deviations from the mean, we can easily interpret the z-score for bell-shaped populations using the empirical rule. When the population has a histogram that is approximately bell-shaped, then approximately 68% of the data will have a z-score between -1 and 1. Approximately 95% of the data will have a z-score between -2 and 2. And finally, almost all the data will have a z-score between -3 and 3. So our outliers are going to be somewhere between this range. Our minor outliers are going to be between 2 and 3, or -2 and -3. But our major outliers are going to be above -3 and 3. So we're going to find quartiles. The software may vary. Excel calculates quartiles differently than the TI-84, and our hand method may vary slightly from both of those softwares. Because the outliers may affect the mean and standard deviation statistics, other non-parametric statistics are used to understand the variable's distribution. Besides the median, which we've already talked about, the quartile statistics break the distribution into fourths. The first quartile is designated at Q1, and as it is at the point where 1/4 of the data distribution is below Q1, which is 25%. The third quartile, designated at Q3, is at a point where 3/4 of the data distribution is below Q3, or 75%. And you recall that Q2, which is the median, has 50% of the data, or 1/2, below and above it. Right? So in our calculations of the median, we remember that the median location is equal to the sample size plus 1 divided by 2. That makes sense, right? And we were able to use that location. If it was a whole number, we would just count. If it was an integer, we would take the number below and above, and we would divide by 2 to get the actual median. But we're going to do something different for the quartiles. So as I said, the methods may vary, but they'll be somewhat similar. The first step is to arrange the data in increasing order. That means sort. Let n be the number of values in the data set. To compute the second quartile, simply compute the median. For the first and third quartiles, proceed as following. The first quartile location is computed by L is equal to 0.25 times n. For the third quartile, third quartile location L is equal to 0.75 times n. So, if L is a whole number, then the quartile is the average of the number in the L position and the number in the L plus 1 position. Slightly different from the median. If L is not a whole number, you round it up to the next higher number, and the quartile is the number in the position corresponding to the rounded up value. So here's an example of finding percentiles. We're going to use the method that we had shown before. The following data shows the HDL cholesterol level of 8 patients. Find Q1, the median, and Q3 in this sorted data set. For Q1, right, since 8 is the number of patients, that's our sample size, we multiply it by 2.5, right, that's 25%, and we get 2, so we get actual values. So according to our rules, we average the second and the third position, the L and the L plus 1 position. So in this case, the second position is 36 and the third position is 37. We add those two together, we divide by 2, and Q1 is equal to 36.2. 4.5. For our median location, the median location was equal to n plus 1 divided by 2, which is this case 8 plus 1 divided by 2, which is 9 divided by 2, which is equal to 4.5. That's what we got. And so the median is, we add both 53 and 63 together, and we get 58. Finally, for the Q3, we get a location 8 times 0.75 of 6, but remember it's a whole number, so we count up to 6, and we get 64, but we have to add it to 74 and then divide by 2, right? So Q3 is equal to 64 plus 74 divided by 2, and that gives us 138 divided by 2, which is 69. So Q3 is 69. So again, the general methods for finding percentiles in general, right, is the percentile location is equal to n, the sample size, times whatever the percentile is, right, in decimal form. And make sure that your sample is sorted. Right. Sample is sorted, and you count if it's, again, if it's a whole number, you would add the location plus the location above it and divide it by 2. If it's an integer, you just round up, and that's the actual percentile. So now we can calculate the 5-number summary. The 5-number summary has the following values: the minimum, Q1, the median, Q3, and the maximum. So in this data set, our 5-number summary is the minimum is equal to 27, Q1 is equal to 36.5, the median is equal to 58, Q3 is equal to 69, and the max is equal to 80. There's our 5-number summary. And that concludes the first part of chapter 3.3. The next part is how we're going to use the 5-number summary to calculate or draw a box plot.